Problem 4 by now should be familiar. It's become a standard problem. It was a variant of this was on exam 3, of course, and variants of it were also on the practice exam before that, and I think in the homeworks. So hopefully there won't be any problems with this one this time, but let's go through it. The problem is to take this system of, in this case, 6 states, quantum states, and find every statistical mechanical thing that's of interest on that particular small system. So first of all, for part A, the problem is to find the partition function. The partition function, of course, is a sum over all the levels, let's say, of the degeneracy for each level times the Boltzmann factor for that level, which in this case is the energy for level 0 here, the ground state here, which is 0, so that's a 1, plus a degeneracy of 2 times e to the minus beta epsilon, plus another degeneracy of 2 times e to the minus beta 3 epsilon, plus e to the minus beta 4 epsilon for the highest level here. At t equals 0, all the betas go to infinity, so q is equal to just 1. Everything is frozen into the ground state. All these other terms become 0. At t equals 2 epsilon over k rather than epsilon over k, and as before, q becomes 1 plus 2 e to the minus 1/2 plus 2 e to the minus 3/2 plus e to the minus 2. And that requires a calculation. Let's see what the answer is over here. It's 2.795. At t goes to infinity, all the betas go to 0, and you just get 1. Q is equal to 1 plus 2 plus 2 plus 1, which is just equal to 6. Part B is to calculate the probabilities for each of the levels, not each of the states. And they are, first for the ground state, e to the minus beta e for the ground state over q, but the ground state energy is 0, so that's just 1 over q. That's 1 over 2.795, which is equal to, well, sorry, take that back. It's 1 over q, and then we'll find the values at the various temperatures next. So let me write that out a little better, and then we can do it systematically. Let me move this down a little bit, and then put t equals 0 there, t equals 2 epsilon over k there, and t goes to infinity there. And so p0 is that. p1 is equal to e is 2, right, because of the degeneracy, e to the minus beta epsilon over q. P2 is equal to 2 again for the degeneracy, e to the minus beta 3 epsilon. And finally, P3 is e to the minus beta 4 epsilon over q. Sorry, I need the q there too. All right. At t equals 0, q goes to 1, so the probability for p0 is 1. All these other guys go to 0, and so it's 1, 0, 0, 0 for t equals 0 for all the probabilities. Everything's frozen to the ground state as usual. At t equals 2 epsilon over k, 1 over q becomes 1 over 2.795, which is equal to 0.3578. P1 becomes 2 e to the minus 1/2 over 2.795, which is equal to 0.4340. Notice that the probability is higher for the second level than it is for the ground state. That's, of course, because there's 2 levels there. For P2, e to the minus 3/2 over 2.795, which is equal to 0.1597. And finally, for P3, for the highest level, e to the minus 2 over 2.795, which is equal to 0.0484. If you add all those guys up together, it's 0.9999, which proves that at least the numbers are reasonable. It doesn't prove that they're right, but at least they add up to the right value. At t infinity, all the exponentials become 1s, and so you get 1 over q. Q is equal to 6, so it's 1/6, 2/6 for each of the degenerate levels, and again 1/6 for the highest level. Part C is to calculate the thermodynamic energy, which is the same thing as the mean energy divided by the level spacing epsilon, and that is equal to, remember, the sum over all the levels of the degeneracy times the energy times e to the minus beta e over q, which in this case becomes, the ground state energy is 0, so the first term disappears, and it becomes 2 e to the minus beta epsilon, 2 epsilon times e to the minus beta epsilon, plus 2 times 3 epsilon e to the minus beta 3 epsilon, plus 4 epsilon e to the minus beta 4 epsilon, all over q. Dividing out the epsilons, that becomes just 2 e to the minus beta epsilon plus 6 e to the minus beta 3 epsilon plus 4 e to the minus beta epsilon, all divided by q. At t equals 0, all the terms in the numerator go to 0, and so we get that the average energy is 0. That's always going to be the case when there is no ZPE energy there. At t equals 2 epsilon over k, we get 2 e to the minus 1/2 plus 6 e to the minus 3/2 plus 4 e to the minus 2 over 2.795, and that works out to be 1.107. And finally, at t goes to infinity, all the exponentials go to 1s. You get 2 plus 6 plus 4 over 6. That's 12 over 6, which is just 2. And that last case is easy to understand because if you look here up at the level diagram again, 2 is right in the middle here. And there's a symmetric set of states both above and below that line, so that's what you'd expect when all the levels have equal contributions because the temperature has gone to infinity and the amount of thermal energy has gone to infinity. All right, what's next? D, finally, is the entropy. As in earlier problems, we're looking for entropy divided by K, and that is equal to the log of Q plus the energy divided by KT, which is, in this case, I guess that's good enough. So at t equals 0, the log of Q is equal to 1, so that's a 0. And the energy is equal to 0. And then energy goes down exponentially, right? It's proportional to e to the minus beta epsilon over kt. So this term wins over that one as things go to 0, and you just get 0. When t is equal to 2 epsilon over k, we get the log of 2.795 plus 1.107 over what? Over 2, I think, yes, for kt when t is equal to 2 epsilon over k. And that is equal to 1.581. And finally, when t goes to infinity, the log of q goes to log of 6 plus 2 for the energy divided by infinity for the temperature. That goes to 0, doesn't count, so it's just the log of 6 that counts. and that's 1.792. Notice that the entropy always rises as T goes up, as is required by the properties of entropy. And that is it for problem 4.